So picking up here where we left off, the this sort of thing isn't the only type of thermometer we can make. We've already talked about another one. The liquid in a tube expands; it takes up a greater volume. What if we had a solid object, though? Would anything happen to it as we change the temperature? And the answer turns out to be yes. And that's what this next slide is about. The change in the length, delta L, is proportional to the temperature change that we subject the object to. And in this case, it's an object that has one really clear dimension along which the same kind of thermal expansion as the liquid in the thermometer occurs. The change in the length is also proportional to the original length, which makes a certain amount of sense if the molecules that make up this solid on average expand so and so far much farther apart. Then if there were twice as many of them, then overall if you add the same amount of space between each one, you're going to end up with a thing that has grown by twice as much. So we can directly proportional to temperature, directly proportional to the original length. We need a constant of proportionality. We need a coefficient of linear expansion. And that's the thing. Let me bring back to the whiteboard just briefly. The change in length is proportional to the original length, proportional to the temperature change, and we've got our constant of proportionality, coefficient of linear thermal expansion. Okay. What if we've got a thing that's expanding along multiple axes? What if it's not just a length? Well, let's think about a cube. The volume of a cube is the cube of the side length. So the rate of change of the volume as the length changes is 3L squared. We take derivative. All right. So dV, there's a small differential change in dV is, well, it's dV, but I could write that with a little bit of chain rule this way, right? The dL's cancel and we've got dV left over, but dV dL is a thing we just said we know. Okay. So dV is 3L L squared dl, but this is the small differential change in length as a result of a temperature change, which we know what it is. It's this thing. It's alpha L delta T. This, I guess, is L0, right? Okay. Right, because that's the length we had before we changed. So that's L cubed, but that's the original volume. So this looks like original volume 3 alpha delta T, and now we've got a new proportionality constant that is just 3 times the old one. Let's call it beta instead of alpha. Beta V0 delta T for volume change. If we allow, excuse me, if we allow normal size changes in temperature instead of differential ones, then we're talking about delta T and we're talking about delta V. I'll let you look through the rest of this section on your own. As fractional expansions, delta L over L0 makes me think about stress. If you took, a rod of aluminum and clamped both ends and then heated it, it would try to expand, but it would be subjected to stress because there are forces trying to push it apart. But we're not allowing it to do that. So we're subjecting it to compressive stress by clamping it there. So that's a tie back to, chapter 11. So I'll let you examine that piece on your own. Let's go back to the slides. One thing to note about thermal expansion like this, if there is a if there is a hole in an object, the hole also expands when we heat the thing. So it's if you've ever used the trick that a stuck jar lid can be unstuck by heating the lid, it's because the ring expands faster than the glass jar does, and so it's easier to get off the jar. So that's just something to remember, that it's not that the hole is compressed because all the material around it expands. It's sort of like it expands from here out, and then the hole actually increases in size as well. And there's the coefficients of volume expansion, and we can see that aluminum is 7.2, 3 times 2.4, that brass times 3 gets us 6, copper 5.1, 5.1 gets us back to 1.7 when we divide by 3. So the table agrees absolutely with our factor of 3 that we ended up with a second ago. Okay, I'm actually gonna chop the end of the segment here. We'll start a new one in a second.